All right, hello and welcome. This is SFU Math 152. It's Brenda Davison. We're going to just take a diversion a little bit into Appendix B of the textbook to talk about complex numbers, because we're going to be using that for the complex eigenvalues, which is coming right after this. So this is, some of you may already be familiar with complex numbers. If you are not, then this is the lecture to acquaint yourself with complex numbers. And if you are, you might want to just listen to this and review it, perhaps stopping the video and doing the exercises yourself. Okay, so let us just talk about how these things can come up. We take a look at the roots of a polynomial function. And we ask the question, does every polynomial function have a root? So if we have some polynomial p of x, is there a number r that makes the polynomial evaluate to 0 at r? So let's just look at a couple of basic examples. Here's a function, f of x equals x squared minus 1. So the roots are the numbers, the values of x that make the polynomial 0, and in this case we could solve for x. We would get x squared is equal to 1, x then is equal to plus or minus 1. So the roots of the polynomial x squared minus 1 are plus and minus 1, because if I substitute either one of those values in for the x here, it evaluates to 0. Okay, so we try the exact same thing now with a different polynomial, x squared plus 1, not looking a whole lot different, only one sign change, and we ask the same question, x squared plus 1 equals 0. We solve for x squared, and we get x squared is minus 1, and that is x squared is plus or minus the square root of minus 1. Okay, that's something you may or may not seen before. Nothing is actually different than what I did before, except now we've got this minus 1 under the square root sign. So what we do now is we define I to be the square root of minus 1. The imaginary number, called I the imaginary number, we define it to be the square root of minus 1. And it is a number such that when I square it, it is equal to minus 1. And otherwise, it has all of the algebraic properties of the real numbers that you know and love. It behaves just like the numbers that you already know about. So for example, arithmetic is associative, it's commutative, distribution applies, all these things. We're going to learn how to add, subtract, multiply them, divide them. They can be solutions to equations, they can be inputs to functions, etc. Okay, so they're working just like the other numbers, but this number is a special number defined in this way. And clearly it's not a real number. So we denote this I is not in the set of real numbers. You know from my previous lectures that that would be not in, and I often write that like that with a double bar, not not in the set of real numbers. Okay, so that is the imaginary number I. Now what we do is we take that and use that to define a complex number. So a complex number, and often we use the variable z when we're talking about a complex number, and it is some real number a plus some other real number b multiplied by I. So the complex number is this number a plus bi, and a and b are real numbers, and numbers of this form z are called complex numbers. And just like we have the set of all real numbers denoted by r, we have the set of all complex numbers denoted by this c with the double bar. So we have the c like that. Okay, if a is 0 in z equals a plus bi, that means that z would then simply be bi, and that is an imaginary number, or a purely imaginary number. It doesn't have any real component, it only has an imaginary component. We can separate out the real and the imaginary component of a complex number. The real part we denote by re of z, the imaginary part we denote by im of z. Real part of z and imaginary part of z. Let's just take a few examples, make sure we understand what that means. So we got to take the real part of z, or some number, this one I've got here, 1 minus 3i. Well, the real part of that is 1. And then the imaginary part of that is the minus 3. Okay, let's do another example. The real part of 7i. Well, there isn't any real part, so the real part is 0. And the imaginary part of 7i is 7. And then if we take another number, 2, the real part of 2 is 2, and the imaginary part of 2 is 0. Okay, so we're just identifying the real part with A and the imaginary part with the number B. Okay, now we're going to proceed to doing a little bit of arithmetic. So we're going to take two complex numbers and add them together. 2 minus I plus 1 plus 2i. Okay, this is totally straightforward. You add the real parts and you add the imaginary parts. So this becomes 3 plus I. Okay, add the real part, add the imaginary part. Okay, we're going to multiply 2 plus 3i by I. We distribute, just like you would in doing any other type of multiplication like this. So you would write this as 2i plus 3i squared. Now we have the additional piece of information that I squared is minus 1. So that's from the definition of what I is. So I squared is minus 1. So then we write this thing as 2i minus 3. 3 times minus 1. And oftentimes we turn that around and write it like this, with the real part first, then followed by the imaginary part. That's multiplying by one number. And then if we're gonna multiply two complex numbers together, like in this third example, we're going to distribute just like the way that you're used to doing it. We would go 2 times 1 is 2, 2 times minus I is minus 2i, 3i times 1 is plus 3i, and 3i times minus I is minus 3i squared. Okay, so then we want to put all these parts together, and we recognize again that we have the I squared here, and I squared is minus 1. So this last term is basically plus 3. So I take the plus 3 from this guy here, I add it to the 2 from here, and I get 5. And then I combine these two imaginary pieces here, and I get I. That is the result there. Okay, so now you can add, subtract, and multiply two complex numbers. So a consequence of the imaginary numbers is that every polynomial can be factored into linear factors. So for every polynomial of degree x, of degree n, every polynomial p of x of degree n can be factored into n linear factors. There are n zeros. Okay, so that's fundamental. This basically is a statement of the fundamental, always a major clue that you should pay attention, fundamental theorem of algebra. Okay, that over the complex numbers, a polynomial of degree n has n roots. All right, next up, continuing with the arithmetic program. So we are going to define this word, a conjugate. You may have already seen this, but in this case, it's going to be a complex conjugate. So if we have some number, z, which is a plus bi, then we define the conjugate, which we denote with this little bar, z with the bar over top, to be a minus bi. So basically the idea is here the real part stays the same and the sign of the complex part changes. Well, that's the definition, that conjugate, or we sometimes would say complex conjugate. Next, so you have to know that word. Next, the modulus. If we have a complex number, then we define the modulus, or the absolute value, as this guy here, which is the square root of a squared plus b squared. It is the length, if you will, of z. Okay, we're going to see how some of these things map quite nicely onto what we've been doing with vectors in the course leading up to here. Okay, so let's just take a few examples, make sure we can understand how to calculate the conjugate and how to calculate the modulus. So if you, good idea, I think, if you're watching the video here, stop the video, do these two examples, and then turn the video back on and check your answers. Way better than watching me do it. Okay, so here I go. Z is 2 minus 3i. So that I can immediately write down what the conjugate of z is. That is 2 plus 3i. W is minus 4 plus 3i, and the conjugate of W is minus 4 minus 3i. Okay, I'll calculate the modulus of Z. The modulus of Z is the square root of the real part squared plus the imaginary part squared. From this example, you should see that the modulus of Z and the modulus of Z bar are the same. Okay, so that in this case is going to be 9 plus 4, that is 13. Okay, and then I'll calculate over here the modulus of W, and that's going to be the square root of minus 4 squared plus 3 squared, that's 16, plus 9, that's 25, and take the square root, it's 5. So the modulus of W is 5. And the modulus of Z is square root of 13. Okay, so we can use this information to show that Z times Z conjugate is the modulus of Z squared. Let's just show that just by computing the left side and computing the right side and showing that they're equal. So here's a number Z, A plus BI. A and B are real numbers. Here is the conjugate, A minus BI. Now I'm going to multiply Z bar, so Z times Z conjugate. That is A plus BI multiplied by A minus BI. And the imaginary part is going to cancel out, and then I will see I'll have A squared plus B squared. Okay, because I have B times minus B, which is minus B squared, and then I have that multiplied by I squared, which is minus 1. So there's Z bar, and then now I'm going to calculate the modulus of Z squared. Well, the modulus of Z is, well, let's just write it this way. There's Z, that's the modulus of Z squared. And then what is the modulus of Z? That is the square root of A squared plus B squared. And then we're squaring that, and that gets us A squared plus B squared. And then we notice, of course, that this is the same as this, so we're done. So we now have showed that Z bar is equal to the modulus of Z squared. Okay, we're going to get some geometric interpretation of this coming soon. Next point, the multiplicative inverse. So if we have some number, some complex number Z, we want to know what number do we multiply it by in order to get the multiplicative identity 1. Okay, so that is the multiplicative inverse. We sometimes, in this case, it is a reciprocal, so we can call it a reciprocal. So it's a reciprocal or a multiplicative inverse. I will tend to use this notation. I much prefer that because that generalizes nicely. Okay, and it is the number such that 1 over Z times Z is equal to 1, or I could write it like this, Z to the minus 1 times Z is equal to 1. So let's see if we can figure out how we could calculate this. So Z to the minus 1 is, well, let's just say what Z is first. Z is some complex number, A plus BI. Then Z to the minus 1 is 1 over A plus BI. And what I'm going to do is multiply top and bottom by the conjugate, like that. And then I will get this, A minus BI divided by A squared plus B squared, which if I wanted, I could break into two components, A over A squared plus B squared minus BI over A squared plus B squared. Okay, so that will get me the reciprocal. I could also use a little bit more compact notation because I see here that this is the conjugate and I see here that this is the modulus squared. So I can simply write this like this, bar over. Okay, but you can always regenerate this. I mean, all you're doing is taking that reciprocal and then multiplying top and bottom by the same thing. So you're multiplying by 1, and the 1 is cleverly disguised as A minus BI divided by A minus BI. Okay, so now we can use that information to, well, we can use it to calculate Z to the minus 1, W to the minus 1, and we can also use it to divide. w divided by z. So let's just go ahead and do that. Again, I'm highly encouraging you to stop the video and do the calculations yourself. Just make sure you've got it, and then you can move quickly along. If you don't have it, then you'll slow down and do a couple of more examples, but check yourself with Wolfram Alpha. Okay, so here we've got z. This is 1 plus root 2i, and then we can calculate the modulus of z. That is going to be the square root of 3. That is 2 plus 1, that's root 2 squared. And then I'm going to calculate the inverse of z. That is 1 minus root 2i divided by root 3 squared. And that is 1/3 minus square root 2 over 3i. So that is the inverse of z. I can do the same thing with w. W is root 3 over 2 minus 1/2 I. So w to the minus 1 is 1 over root 3 over 2 plus 1/2 I. Multiply top and bottom by the conjugate. Like that, and I get, you do the arithmetic and check me. Yeah, I'm known to sometimes make arithmetic mistakes, so check this out. This is what I got when I did it. So you make this calculation, and I got this as my inverse. You can see that the bottom is 1. That's a nice feature. By the bottom, I mean this denominator here. Okay, so now I have z, w, z to the minus 1 and w to the minus 1. And so now I'm going to take w and divide it by z. And that is the same as taking w and multiplying it by z to the minus 1, which I already know what that is. So I'm going to take w, root 3 over 2 minus 1/2 I. I'm going to multiply that by z to the minus 1. Because I've already calculated that. So this is how I can do division. I don't sort of have the normal mechanism I would have with numbers of doing quote like long division or making it to a fraction or changing it to a decimal. What I think to do when I want to do division is what I want to do is take the number in the numerator and then multiply it by the multiplicative inverse of the number in the denominator. Okay. So I've written that out. Then there's the usual distribution and arithmetic. Why don't you do that? Do the arithmetic yourself, check. What I got when I did that was root 3 plus root 2 over 6 plus 1 minus root 6 over 6 multiplied by I. Okay, so go ahead, do that distribution and collect like terms and see that you get that there. Okay, the next point, we can think about a complex number, z is a plus bi, as being represented by a point, ab, in the R2 plane. Now, so in some sense, you could think of it as like a vector in R2. So we've had this issue come up before. So let us look at now, we've now got 3 flavors of the same thing. Sometimes we think when we see a pair of numbers like this in the brackets there, we think to ourselves, okay, that is a pair of numbers. And how are we thinking of that pair of numbers? Well, one way that we sometimes think of them is this point. We think of it as a point. The point P equals AB. Sometimes we've been thinking of that as the vector. The vector, maybe say, let's just call it V. AB, like that. Now we could be thinking of it also as a complex number, Z equals A plus BI. And how you're thinking of it, so that could also be written as Z is AB. So how you're thinking of this AB, when you just see this, which way you're thinking of it, this is going to depend on the context in which you are using it. But basically, it is just 2 real numbers that you are going to use, and it's always in different ways, perhaps, but they're always located in the same place. So let us just draw our situation here. What we'll be if we're thinking of it as a point, we would just do our usual thing. We have our x and our y axis. We go along here 3, and we go up here 2, and then we locate the point right here, 3, 2. So my example here is going to be the point 3, 2. So I'm talking about looking at this thing here. Okay, if I'm thinking of it as a point, I put the dot there on the xy plane, and I could label that there. That's the point 3, 2. Okay, that is now, it's going to be, of course, in the exact same location. The other way I can think of this, though, is I could locate the vector v, whose terminal point is 3, 2. So I could be thinking of it that way as well. Then the other thing I could be thinking is that I'm thinking of 3, 2 as a complex number, and I denote this as, in this case I have x and y here, and I can denote this as the real axis and this as the imaginary axis. I come along here, there's 3, I come up here, there's 2, and I put the thing right here, and then this is z equals 3 plus 2i. Okay. Okay. When I'm thinking in this way, in this representation, I mean these things are what we already know. Adding and subtracting complex numbers corresponds to adding and subtracting the equivalent vectors. Multiplying a complex number by a real number, let's be careful, this is a scalar, corresponds to multiplying a vector by a scalar. Okay, careful, caution. Multiplying two complex numbers does not correspond to either the dot product or the cross product that we've been seeing with vectors. Well, we haven't actually seen the cross product yet, but we've certainly been using the dot product. Okay, the modulus, what we just saw just a second ago, the modulus corresponds to the norm of the vector. And then the vector representation of a conjugate is the vector of z reflected across the real axis. So let's just draw this one here. I could imagine putting a vector here like that, and then if I look at what is the conjugate, that is, well, z bar would be 3 minus 2i, and so I would go down here to minus 2, and that would be here, and then that's going to be right here. So this is z, well, it's z bar there. It's that right here, z bar 3 minus 2i, and you can see that when I have that to the best of my drawing abilities there, when I have the vector drawn there, I am reflecting it across the real axis, or the x-axis. Okay, so let's take a look at some of the properties just written out here as a theorem. Properties of the conjugate, the modulus, and the multiplicative inverse. So I'm taking any two complex numbers, w and z, and then these facts are true. The conjugate of w plus z is the conjugate of w plus the conjugate of z. And so you can read through these. All of them have a variety of properties here. What I suggest, I strongly recommend as an exercise for you, take two numbers. Take, I don't know, let's say just take z equals to 1 minus 2i, and take w equal to 2 plus 3i, say. And do all these computations on the left-hand side, on the right-hand side, and at least show yourself with this example that these statements are true, and then make sure that you can, that'll also ensure that you can do all the calculations. Okay, so perform all this, do all these computations, do all the computations. And check. This will ensure you understood the arithmetic so far, and that you get some practice with these things. Okay, next point. So far we've been having the representation of the complex number a plus bi in the rectangular coordinate system, and what we can do is have a polar form of the complex number. Okay, so let us take a look. We define phi to be the angle from the real axis to the vector AB, and then we can write the real and imaginary components of z. Now let's remember that z is a plus bi. So I can it is the case I can write the real part of z, which is a. This right here is the real part of z, and then the imaginary part of z, which is b, and if I have that angle phi from the from the real axis to the vector AB, it is the case that A is equal to the modulus of Z times cos phi, and B is equal to the modulus of Z times sine phi. This perhaps does not come as a surprise. Let us just quickly draw an example here. There's the vector going to the number there, and I've defined this angle here to be phi, and this height here is B, and this distance here is A, and then you could see, and then right here on the hypotenuse, that is the modulus of Z. So we have that you can see that sine phi is opposite over adjacent, and cosine phi is, sorry, opposite over hypotenuse, and cosine phi is adjacent over hypotenuse. And then you just multiply both sides, and you have these two statements right here. Okay, so then when we now we have A and B expressed in this way, then we can express the complex number itself as the modulus of Z times cos phi plus I sine phi, and that is called the polar form of Z. And the angle phi is well, it's not the, because there's more, it can be more than one, is called an argument of Z. Okay, so we have expressed this thing expressed differently, but it is the same place in the complex plane. It's the same point on our two-dimensional plane. Okay, so one thing to notice when we choose to do this is that the angle is not unique. So for example, phi, whatever number phi that is there, phi could also be this guy here. So we can always add these multiples of 2 pi. And then, so if we restrict phi to be in this range between minus pi and pi, then that gives us what we call the principal argument of Z. Okay, the argument is that angle. So if we restrict it within there, then we call that the principal argument. Okay, what we're going to do now is we are going to write out a couple of numbers in polar form. We're going to change them to polar form, and then we're going to compute the product and the quotient of the two numbers, and we're going to take a look at what these things look like in the complex plane. So before we even get going, we can plot W and Z to see where they are and what they look like. So let us do W first. W is root 3 plus 1i, so that is going to be root 3 is about 1.7, so it's going to be like about right here, right about here, like that. That is W. And then where is Z? Z is 1 plus root 3, so that is the 1, the real part, and then root 3 is going to be somewhere about here. So that is going to be Z. Okay. All right, so I'm going to just draw a line to W. And draw like that to Z. Okay, just see those two things. So maybe make it a little bit clearer exactly where they are. Okay, so we have W is root 3 plus I. Now we want to put this into polar form. So the magnitude, the modulus of W is 2. That is root 3 squared, which is 3, plus 1 squared. So the modulus of W is 2. The conjugate of W is root 3 minus I. So we could just put that on here just because it's kind of fun. That is going to be right here. That is going to be the conjugate of W, for example. Okay, so in this case, for W, A is equal to root 3, and B is equal to 1. Now we want to determine the angle here, this angle here for W, this angle phi. You can see that the sine of phi is 1/2, and that the cosine of phi is root 3 over 2. And this is telling us that phi is pi by 6. Okay, so I know that angle phi is pi by 6. Okay, next thing I'm going to do is the same thing for z, possibly in just a little bit less detail, but we have z equal to 1 plus root 3i. So again, make these calculations yourself. Make sure you can do this. Z, the conjugate of z is 1 minus root 3z. The modulus of z is equal to 2, and the angle for z is equal to pi by 3. Okay, so I've figured out. I'm just going to erase. A second, I'm just going to erase this guy right here. Erase him. I'm going to put the actual angle there. So we've managed to figure out that this thing right here is pi by 6. And then do this angle here, and I found out that that one is pi by 3. Okay, this is Pythagorean theorem. That's it. So I've got pi by 6 there and pi by 3 there. So I could write now w and z in their polar forms. They will look like this. W, which is root 3 plus I, can also be written like this. 2 times cosine pi by 6 plus I sine pi by 6. So that is the polar form of W, the second one here. Okay, similarly, I can do the same thing for Z. Z is equal to 2 times the cosine of pi by 3 plus I times the sine of pi by 3. Okay, so that is W and Z in their polar form. Now I'm going to compute W times Z. Okay, and I'm going to do it using complex multiplication that we just saw. So that looks like this. That's W, not in its polar form. And here's Z, not in its polar form. And I'm going to multiply those two things together. And what do I get? I get 4i. Again, please do the multiplication and check me. Okay, now let's just take a look at what would could I just write this down, for example. And now I'm looking at the polar form of this W times Z, and I'm looking at this, and I'm noticing that, and this is generally true. It's not just here, that the 4, this I've got the modulus, for example, here the modulus of W Z is 4, and that is in fact this modulus times this modulus. So I could take that 2 times 2 and simply write down the 4 right away. Then I'm noticing I only have an imaginary part, and I might be able to see that in this way. Cosine of what? Cosine of pi by 6 plus pi by 3 plus I times the sine of pi by 6 plus pi by 3. Okay. So, and this thing is 0. That's the 90-degree angle. So that thing right there is 0. So that the phi in this case is 90. So I would generally you wouldn't see it like this. You would whatever, but I want to make this clear. So that's cosine pi by 2 plus I, there's a bracket there, I sine pi by 2. Because let's see where that is. That is right up here. 2 times 2. I'm just going to make sure I do this correctly, is 4. So let me draw that here. Let me draw this 4i. Basically, we know it's 4i, so it's right here. I want to get another color. It is right here. Okay, 4i is right here. This is 4i. Okay, so what is that? I have multiplied, it's the magnitude of W times the magnitude of Z, and it's also, it's the sum of the angles. So it's as though I took W and in fact it rotated it by Z. So it's the sum of the two angles. So I've basically, when I multiply W and Z, if I have them in their polar form, I can simply multiply together the modulus, and I can add together the two angles. Okay, let's do the same thing with the division. See what happens. Okay, we're going to take W divided by Z. Okay, we could do this in the rectangular coordinates this way, like that. Please go ahead and do this. Okay, you can multiply by the conjugate and whatever. You need to practice if you haven't seen this too often, and practice is always a good thing. Okay, so there I can do it this way. Then I could compute the modulus here of this thing, which would be the square root of 3/4 plus 1/4, and that is 1. And you'll notice that 1 is equal to 2 times 2. So the modulus of w over z is the modulus of w divided by the modulus of z. Okay, and then let us take a look at what the angle is here. The angle there is minus pi by 3. And minus pi by 3 is in fact pi by 6 minus pi by 3. So the angle that I got for here, the angle for w over z, and I could write this like this: the argument for w over z is equal to the argument for w minus the argument for z. Okay, which is that number 5 for the given complex number. Okay, similarly above I had that I added the arguments together and I multiplied. When I multiplied the modulus and I added the arguments. When I divided the moduluses and I subtracted the arguments. This is generally true. Let us take a look at where w divided by z is. We know that it is 1 at an angle of minus pi by 3. So it's here. It's 1. This distance is 1 at an angle of minus pi by 3. So, sorry, did I say pi? That can't be right. Pi by 3? Is that right? Yes, minus pi by 3. Hang on, something appears to be wrong. It's not minus pi by 3. It is pi by 6. Hang on. This is this is an incorrect algebra. Pi by 6. Okay, hang on. Pi by 6 minus 2 pi by 6 is equal to minus pi by 6. This should be here, pi by 6. It can't be pi by 3. Sorry about that. Pi by 6. I managed to subtract wrong. Okay, so I'm here, and I see that it has to be here minus pi by 6. That's where I realized I had made an error. So it is right here. It has a length of 1, and it's a half and minus a half and root 3 over 2. So that is right here. So that is w divided by z right there. Okay, so they have a geometric interpretation. Okay, so here's that thing, what we've just done in an elaborate example presented as a theorem. Okay, we have one complex number z1 in its polar form, and we have another complex number z2 in its polar form. If we multiply them together, we multiply the moduluses and we add the two angles. Okay, if we divide the two moduli and we subtract the angles. Okay, so let us just take a look at a really basic example to kind of see what's going on. And I think this is actually really kind of neat, and it's sort of a big idea to get this idea about scaling and rotation into your head. So scaling is when we make, we take a vector. We've seen this in vectors typically, and we multiply it by something. We stretch or shrink it, and then also we can rotate. And let's just notice what happens here. What is the geometric effect of multiplying a complex number by I? Okay, so let's take the number 1 there, and then let us multiply. Okay, so we're starting here with 1. And then we're taking 1 and multiplying it by I, giving us I. We're here, because that's where I is. Okay, so this is a real axis, and this is the imaginary axis. So the effect here was to rotate by 90 degrees. Now I'm going to take I and multiply it by I, and I get minus 1. That's here. So now multiplying by I, it did it again, right? And multiplied it, rotated by 90 degrees. Now I take the minus 1, multiply by I, and what do I get? I get minus I. That is here, minus I. So I again have rotated by 90 degrees, and I'm rotating in the counterclockwise direction. And then I am going to do the final thing, take minus I, multiply by I, get minus I squared, I squared is minus 1, so that is 1. So I have multiplied and I'm back. So each time I multiply a complex number, in this case my complex number was simple, it was just a number 1, but this is true for any complex number that I take. If I take the complex number, I multiply by I rotate by 90 degrees. And you'll notice that, say, if we go back into where you may have been in grade school, if you had, for example, the number 2 here, and you said, what happens if I multiply 2 by minus 1? You would say, oh, it flips over to here, right? How much better to say, oh, if I multiply by minus 1, I rotate by 180 degrees. Because then now that if we had that language in place earlier on, rather than flipping, we would be thinking of rotating by 180 degrees, then it would seem to be more natural to say, oh, this is then a rotation of 90. And you'll notice that by taking the square root, I am having the rotation amount. Okay, so this was, the 180 was multiply by minus 1. And then the 90 degree rotation here is the multiply by the square root of minus 1, which we've been calling I. Okay, if you divide by I, what happens? Let's have a look. Just try it out. We start here with 1, and we ask what is 1 divided by I. In order to figure that out, we multiply top and bottom by I, and we get I over I squared, and I squared is minus 1, so this is minus I. So you're going down here like this. So it's rotating by 90 as well, but it is in the opposite direction. That's what you usually anticipate a negative sign to do. Do the same thing, yeah, but do it in the opposite direction. Okay, so then let us take minus I and divide by I. That gives us minus 1. So I'm here, minus 1. And then I take minus 1, divide by I. And to do that one, I multiply top and bottom by I. And what do I get? I get minus I over I squared, which is positive I. It comes up here. That's positive I. And then finally, I take I divided by I, and that is 1, and I rotate back here. So this is, both of these, multiplying or dividing by I, rotates you by 90 degrees. And then which one is multiplication? Rotating counterclockwise, and then division is rotating clockwise. Okay, some complex numbers, and next lecture up we'll be finding eigenvalues and eigenvectors, and then we'll be able to allow complex numbers in to those calculations, and we will be able to handle them. See you next time. Bye.